Okay, so first of all, I'd like to introduce you a little bit to my research center. I want to point out that this is an international center, so we are the International Center for Advanced Internet Research. We're part of Northwestern University. We are affiliated with the McCormick School of Engineering and Applied Science. What we do is large-scale transport infrastructure. So we do a lot of work in optical networking, layer 1, layer 2 networking. I'd like to note also that we're a little bit different with regard to research in that we not only create new technologies, architectures, we also operate a lot of test beds. At any given time, we're managing anywhere between 15 and 20 major national and international test beds. We also run production networks. Most of these are oriented to data-intensive science, so we create private networks. This is a context slide to present a macro view of a major paradigm shift that's going on in communications. Since communications have developed many years ago, we have had what's represented here by a carrier cloud and so-called managed services. What that means is that someone in advance has decided what a service is, how it should be provisioned, what are the technologies and architectures, and how it should be supported. That's been the world since the telegraph, the telephone, probably semaphores that were used in the 1800s. That's all going away. What is changing is through higher levels of abstraction, which have driven all the major revolutions in information technology, is what's represented here on this slide, which is that instead of people predetermining the types of service and technologies, you as an individual can go into a vast pool of resources and find the resources you want, collect them together, and create your own services. So you heard about the Genie project. Well, Genie is doing that today. Genie is allowing individual students and faculty members to create their own private networks, unique networks. They don't even necessarily use TCP/IP. So right now it's being used primarily by researchers, but this is going to gravitate out into the wide world as all these innovations do. This is the way communications will be handled in the future, highly customizable, sort of like a phone app today, but a phone app that you can create and implement. So there's a lot of macro network science themes required to bring the next level of innovation forward. You heard a lot about programmability from Mark, and that's certainly one major theme. And the one reason that you can do that is the higher level of abstraction that's possible today through network virtualization. There's another major theme that's maybe equal, which is capacity. So in addition to programmability, capacity is driving a lot of what needs to be done in networks. We currently run an exchange, an international exchange that has 2,900 gigabit per second paths, and that's constantly increasing. So we're in the world of 100 gigabits, and now terabits are being researched. So there's two themes. One is capacity, the other is programmability. With regard to the international, I'll note that there is an international community working on this. It's called the Global Lambda Integrated Facility Community. You can see it here. This is a community of network researchers and network production engineers that collectively have put together this distributed facility. It's not a network, it's a facility within which you can create private networks. Many of these are being created for data-intensive science projects, but they're being created for other types of activities, including network test beds. And I'll note that over here we have, you can't see it because of the size, Moscow Light. So Moscow is participating in this. Russia is participating and has for many years. So I have now an arrow there. And we've worked with Ruslan and a number of projects, including Genie projects, one called Slice Around the World. And we've worked with other partners in Russia for a number of years on a number of different projects. By the way, regarding Ruslan, I'd like to thank him for putting together this very nice conference, and a special thanks to Roland for all the logistics he's done for the conference. There's another joint project in which we've been involved, which has Russia as a partner, and that's called Gloriad, and you see it here. Gloriad started some years ago as a partnership between the US, Russia, China, later joined by Korea, Netherlands, Canada, Scandinavian countries. This is another partnership that is developing worldwide resources that are increasingly programmable for the research and education communities. More recently, a node has been installed in Singapore, another in India, and Cairo. So it's continuing to expand and is part of the Glyph community. So the Glyph community has, for many years, began developing a network service called the Network Service Interface. You've heard that referenced a couple times earlier. The Network Service Interface architecture is being standardized within the Open Grid Forum, which is a standards body, to enable path resource sharing among Glyph exchange points with multiple control frameworks. It's based on federated architecture. And these are some of the participants in the automated goal fabric, which is moving this forward. For the last 5 years, it's been demonstrated, it's been experimented with, and now it's moving into production networks around the world. This is a goal demonstration that was auto goal demonstration that was put together for supercomputing last year. And these are the automated goal backbones. This is our organization in the middle of a bunch of VLANs that are highly programmable and allocatable. To date, the Network Service Interface has not been integrated with SDN and OpenFlow, so our organization has undertaken the task of doing that. There's another project that Jerry Sobieski, who will speak in a bit, is undertaken also to integrate NSI with SDN OpenFlow. Within Genie, we've been working on something called the International Genie, and we're now migrating that to SDN OpenFlow at sites across the world. We have this OpenFlow testbed that's up and running now, and notice we have also incorporated a node at the Applied Research Center for Computer Networks as part of this fabric. So this is a worldwide fabric for network researchers, for network scientists, and the slide shows you some of what's being done with it. Each color represents a different research community doing a different project with resources throughout the world. Sometimes these are demonstrations, sometimes the research experiments, but the point is that you can slice these fabrics and do different things. This was a showcase done for the Supercomputing Conference SC13 last year. We worked with Genie to implement this fabric. These are Genie racks in different campuses. Each rack is basically a cloud with an internal network and an external uplink network, and it's available as a resource through these international federations that Mark talked about. So what about SDXs? Well, SDN, software-defined networking, is basically taken over much of the networking world because they're more programmable. However, right now, SDXs and architecture and technology is single domain oriented. So that raises an issue. What's happening really is the collection of a bunch of SDN islands. So the primary motivation initially for an SDX was to connect the islands of SDNs. However, there are other motivations. For example, in the US, the White House Office of Science Technology Policy believes that these are good for large-scale science instrumentation. And also, the digital media community is interested in using these for specialized digital media exchange services. There are additional uses. Another big motivation has been that you can do far better traffic engineering with a software-defined networking exchange than you can with a standard exchange. And you can implement network function virtualization in such an exchange. So there's a lot there. One thing that interests us is large-scale science projects being served by SDXs, because that's our community. Our primary clientele consists of large-scale science projects. We support hundreds worldwide. One large one I'll point to is the Large Hadron Collider, which is a collider at CERN. This is the private network that was created to serve the top-tier, Tier 1 computational processes. This is a worldwide private optical-based network called the Optical Private Network. This is another network that we're building now in quasi-prototype. It's called the Large Hadron Collider Open Network Environment. As you can see, there's sites throughout the world. One of the participants in this project is Russia, the Russian particle physics community. So basically, the SDI part of SDXs is extending these capabilities to infrastructure, clouds, grids, supercomputers, clusters, instruments, sensors. We're also doing that. An earlier speaker noted that this university was oriented to high-performance computing. It's another community we serve. The petascale computer science facility, which is the largest petascale science facility supported by the National Science Foundation, is in our neighborhood, and we take care of much of their networking. Another related project is called Exes, which is a distributed grid of supercomputing centers on a private network. We're continually working on capabilities for high-performance clouds. We formed a consortium to investigate that. There's also something called the Open Science Grid. As part of that, we're working on methodologies to isolate science traffic from other traffic because of their large-scale flows, which seems to be, which is disruptive with regard to smaller flows that are generally supported by consumer networks. We're interested in SDXs and SDIs for that particular purpose. Another motivation comes from the consumer services such as Google. This is their software-defined wide area network. It's, again, a silo, and they're interested in expanding that out. They believe that they would like to create a software-defined exchange. So today, there is no such thing as a software-defined exchange in production, but we have some ideas, we have some concepts. I'm not going to go through the attributes, but I assume these slides will be somewhere. They're basically highly programmable. We have one which we're working on in partnership with the Genie project at our Starlike facility, which is an exchange for data-intensive science. There's 130 private networks there. At the highest level, it appears to be a very large-scale virtual switch. It's based on a foundation of physical resources. This is what it looks like as a series of physical resources. We have interfaces to the resources there. And we have been running some demonstrations of this. One we did in partnership with Mike Zink there, who will be talking in a bit. He's been developing something called Nowcast as a weather prediction application. It gathers a huge amount of data so you can see weather better and predict weather better. However, because of the amount of data it's gathering, you can't store it locally, or you can't compute it locally, or visualize it, or do the analytics. So you need to send it across the country on high-speed networks for those functions and send the results back. Here's a Nowcast example. On the left, you can see a highly granulated weather system compared to the old Doppler radar on the right. So it's a very nice technology, and it requires dynamic topologies. And this is the scenario that we did as a demonstration for the Genie 19, the Genie Engineering Conference in March, showing the dynamically provisioned light paths, or VLAN paths. We also did a demonstration for Torina earlier this year in May, connecting our nascent SDX at Starlike with one at Netherlight in Amsterdam. And for the Global Lambda Grid workshop in New Zealand recently, we worked with many people throughout the world on doing a provisioning of Mike Zink's Nowcast. This is the data plane that we put together among sites around the world. These are some federation attributes that we were bringing into this and had planned for GDC 21, which took place with our partners in Japan. These are sites in Korea, in Canada, in Taiwan, and we're now beginning to develop some additional SDX initiatives, because even though the motivation of the SDX has been to remove the siloing effect of SDNs and to do better traffic engineering, it turns out that you can do a lot more with SDXs. You can create, for example, customized exchanges for particular sciences or other applications, such as high-end digital media. We're planning to showcase some of these for the Supercomputing conference in New Orleans in November. This is a national testbed that we have provisioned, a 100 gig testbed that this will flow on. So one of our areas is coupling the programmable capabilities of SDXs with 100 gig flows, including for genomics. We've been working on a project with the National Institutes of Health. This is what we showed last year at the Supercomputing conference. This year, one of our demonstrations is going to be a customized Bioinformatics Exchange built within an SDX. So within an SDX, you can be recursive. You can have many internal exchanges that are customized within your large virtual switch. So the flows for computational biology are very complex. Some are very large, some are very small. They're constantly changing. And we think that an SDX Bioinformatics Exchange is a perfect solution for them. And again, we're going to showcase this prototype for the first time at Supercomputing. We're also working with Jerry Sobieski, again, who will speak shortly, on extending this capability to a research testbed on demand service that he's developing. Another project that we're going to integrate this capability to is a distributed cloud testbed called Chameleon, which is being funded by the National Science Foundation. And with that, I'll say thanks to all of our international partners, and again, thanks for the opportunity to be here, and I'll take any questions you may have.
Please, questions? Okay.
First of all, thank you for the presentation. It was really nice. I have a such question. You said your future plans is to make a united system of different testbeds, including Genie, Exes, and other testbeds. you plan to standardize the APIs, or you plan to build some sort of Starlike operational system? And what's your opinion? Is such heterogeneous system need an operational, or we need only to stop on the standardizing APIs?
Okay, those are...
John, let me add to this question. It's very interesting questions. In the context of Mark presentation, SDEx, it's a meeting point of federates, where they have to negotiate about the resources, about the policies, etc., etc., etc. So, more or less I can understand we can do this in a flat network without any hierarchy. But how you can do this if you have a hierarchy within your network where there are several carriers, operators, etc., etc.
Okay, so that's a very long series of questions with many key issues. So what it boils down to essentially is similar questions to what Mark was bringing up. How do you achieve the federation? Because you do have different classes of users, you have different classes of carriers, you have different classes of services, you have different types of resources and many different policies. As Mark said, some people don't care. They'll provide a resource and they won't care about who's using it or how much it's being used. Other people care a very large amount. So you have different value systems. Okay, so all these are truly issues. However, these international networks that appear today have been working on these issues for 10 years. So it's not as if they're brand new issues just being discovered. We have this very nice NSI example that's going into production. These are different networks. They're federating. They're using each other's resources. They have, in fact, used each other's resources for many, many years. The only thing that's different now is that process that used to be highly manual is moving toward software and automation. With regard to the question about one API, I think that it's not possible even now to think about one API. There will be several APIs. However, I'll note that NSI is an API. And the reason that it was created was that each of the goals, the glyph exchange points, had a different control framework. So in order to use it, you didn't want to have someone learn 10 different control frameworks. So NSI was created. That was the original motivation, to have one API talking to those control frameworks, and it's been successful to that degree for talking to many different federated networks. So the grand vision isn't done yet, but we have done a lot and are continuing to move this forward. It just takes cooperation among the international communities, and I think we have that. With regard to Starlight, you said, are you going to somewhat expand Starlight? Starlight is one resource among many. So you saw on those maps many exchange points, including Moscow Light. They're all peers. They're all going to be federated. They're all becoming increasingly federated.
Thank you, Joe. Let me come to the same question from the different side. I have some philosophical idea that there are a lot of common between human society organization and computer networks and informational system organizations. We can find a lot of common. And we also have a human society, a lot of kind of policies, regulations, etc., etc., etc. And a huge amount of the different kind of interfaces and huge bureaucracy which should enforce that everybody should follow these policies and regulations. So human society spent a lot of efforts and resources in order to solve this problem. So what's about networking? You remember at the beginning of the operating system, one of the key index about the quality of operating system, how much of computation resources operating system spent for itself. So what is your opinion? Maybe such sort of regulation and policies will consume a lot of resources from our networks.
Well, certainly you mentioned some major challenges, and I like your description of the world of people and the world of networks. Living in the world of networks, I find the world of networks to be easier than the world of people. When you get into psychology and sociology, it's a thicket of huge challenges. In the world of networking, 1 and 1 equals 2, and you can be happy with that. So yes, these wider social issues will intrude on the networking space. An observation about that, though, is that one reason for the great success of the internet has been it has been outside the scope of that regulation. The regulators were all regulating the telephones because they thought they were so important. They sort of ignored the internet, and it grew up unregulated, which is now an issue today. But it would not have been as successful as it was if the armies of lawyers had come in with their armies of policies and policy committees. It's very toxic to the innovation process. So hopefully with innovation we can continue to move without that heavy-handed regulation, but yet be good, responsible citizens. We want to do that. And I think that these new tools that we have, for example, deprogrammability of the network, are going to address these issues. You can have more secure networks if they're more highly programmable, if you know what's going on, if they're better monitored, and you have tools that reach deeply into the network, as opposed to having types of networks that are one-size-fits-all type networks. So we're solving both problems at the same time.